So if you have a system of linear inequalities representing constraints on some system, and you have some linear function that you would like to, say, maximize with respect to those constraints, this is not incredibly hard mathematics. We teach a method for it in our 139 class. Is somebody else trying to get in? We teach the Simplex Method for it, which is actually sort of the industrial standard for problems of this kind. And the difficulty with it, the dirty secret about it is that you can't really do it, at least not in reasonable time. Worst case computational time for the Simplex Method is exponential time in number of variables. It's really, really horribly time consuming. There's no way you can do that at an industrial scale, except that people do. The secret to it is that you have to be fantastically unlucky to get one of those bad cases that takes so long. Most cases that you practically encounter, you can run the algorithm and it terminates and gives you the answer pretty quickly. That observation is the inspiration for all of this. What does it mean to think about whether you have algorithms for something in a world where you want to say, well, yeah, practically, we're probably not going to get so fantastically unlucky as to hit a zero probability set. If the bad cases have probability 0, if you give me a random case, it's probably not going to be one of those. So, what I mean by this, if you know what a group is, this may or may not look like one. If you don't know what a group is, what I'm about to tell you will suffice. So you take these letters, and you take formal inverses to them, and you take a formal element 1, which is the same as not writing anything at all. And then you start writing words in these letters, A, B, A inverse, and B inverse. Write all the words you can. And then for everything on this side, you get to collapse any instance you see of that word. Collapse that down to 1. You always get for free the relations AA inverse and BB inverse. So Dane proposed this thing commonly called the word problem. Given a thing like that, where you have finitely many generators and finitely many relators, figure out if it reduces. Figure out if it's equal to the identity. So for instance, in this group, if you start with this one, you can start fiddling with it. I don't propose to actually work through the reduction. This one, because this says in effect that A and B have to commute, you can actually fiddle with this word and see that it's equal to the identity. In fact, this group is z plus z, two copies of the integers, direct sum with one another. For a general group, if you just write down some random letters and write down some random words in them, write down some random reduction rules over here, it may be very hard to tell whether it's going to reduce. Now, when Dane stated this problem, it was early enough that it was not at all clear what a negative solution to this could look like. I mean, a positive solution is, here's the algorithm. You give me the presentation, here's what I'm going to do with it to figure out whether the word is the identity or not. A negative solution is harder.
You mean for a particular word or algorithm for all of them?
So this asks, the way I've stated it here asks for an algorithm that will look at a group presentation and a word and determine if it's the identity. You can also talk about, for a particular group, is there an algorithm that you give it a word, it will say it's the identity or it's not. Now, not looking for a way to write a negative solution to this, but for other reasons. In the 1930s, there were 6 or 8 people in various parts of the world, a lot of them not initially in communication with one another, that all tried to define the same thing. They all tried to define what a procedure was, or an algorithm, or something like that. And they all came up with absolutely equivalent definitions. Each of those definitions is an interesting lecture in itself, and oftentimes there are quite a lot of symbols involved that take quite a lot of defining. All of the definitions are equivalent to this, and I feel comfortable saying that no matter what your favorite computer programming language is, it's equivalent. When you have a bunch of different definitions from different people, not initially in communication with one another, a bunch of different definitions of the same thing, and they all come out equivalent, that does seem to be some evidence that they got something right. Well, so once you know what a computable function is, you can also define a computable set by saying that this indicator function, this characteristic function is computable. You give in to your program, and it will tell you, yes, it's in, or no, it's out.
So within some known or assumed time, or?
Nothing on time, finite time. It has to answer. Your computer program has to run, and it has to return a value. That's it. So we say that a set's computably enumerable if it's the range of a computable function. What that practically means is that you can list off the elements. You can write a program that will list off the elements. What it does is it takes that function whose range S is, and it says to the program, okay, evaluate f of 0. Now evaluate f of 1. Now evaluate f of 2. Now evaluate f of 3. And in this way you'll eventually list stuff off. You never have evidence that something will not be listed off. If you haven't seen 7 yet, that's no guarantee that you won't see it someday listed off. So there are computably enumerable sets that aren't computable. So the big result on the word problem is that it's not always solvable. You write down the right collection of generators, not such a big deal. Write down the right collection of relators, very big deal. Write down the right collection of relators, and you will have a group so that no computable function can look at words and say, yes, it's the identity, or no, it isn't. Back to that simplex algorithm. In this group, in this example they picked, you have to get fantastically unlucky to find a word that cannot be handled by some obvious means. Most of the words that you look at are words that you can compute whether it's the identity or not. You not only need the right group, you really need the right examples in that group for the algorithm not to work. Page 2, that's not page 1. Fast forward about 50 years, about 2003. I'm going to give the second condition momentarily. But what we're asking here is not that the characteristic function itself be computable, but rather that there be this other function that's computable and matches at most places. This function phi may not be defined on all of the natural numbers. That's what I mean by partial. It's only defined on a subset of the natural numbers. But wherever it is defined, it agrees with the characteristic function. Now the second condition. This second function, or the second condition, says that phi is defined almost everywhere. In particular, if you take the places that phi is defined up through n and divide by n. So places it could be defined, places it is defined. That should go to 1. So for instance, if phi is defined exactly on the even numbers, this is going to go to 1/2. You look at 0, okay, it's defined everywhere. You look at 0 and 1, well, it's defined half the places. You look at 0, 1, and 2, it's defined 2/3 of the places. 0, 1, 2, 3, a half. Keep going out farther and farther, it settles down to a half. What I want is for it to settle down to 1, which means that it's defined really, really most places. This is at least one version of the almost in the title of the talk. So S may not be computable, but there's a computable thing really close to being it. If you have worked some in algebraic number theory or something, you may recognize this is the natural density. They have a name for this. Do that same calculation on the symmetric difference between S and T. That should go to 0. What this means, to be coarsely computable, means, well, you're not a computable set, but your brother is. Your twin brother is a computable set. There is another set that's computable that is so much like you that the places where you disagree are very rare. These two are not equivalent, and as far as making up examples goes, you can make up examples to show that they have about as little to do with one another as you would care to name. So this was the paper for which the definitions were put together. So when I told you that in this example you have to get fantastically unlucky to find the counterexample, to find a word that it won't work on. This quantifies that. And it really didn't surprise anybody because people knew the example was contrived and they knew that the words that would give you unsolvability were hard to find. They proved, in fact, a lot more than this. They gave several characterizations of groups, and most of the theorems in that paper go, let G be a group such that mumble, 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 then G has word problem, and most of them, including these two examples, the word problem is generically solvable in linear time. So you not only can compute it, but you can compute it really, really fast. Which is a whole lot better than not at all ever. Chapter 3. Groups are hard. Groups in general are very hard. And so, if you want to go out past examples and start theory building, you usually want to work with some particular class of group. And it turns out that that it is at least one useful direction to go to start thinking about Abelian groups. Groups where everything commutes. Those are at least easier to work with. Now, you have heard of the first-year student on campus who one evening was crouched down next to a sidewalk, looking along the ground carefully. The professor came by, said, "What's wrong? Can I help you?" Student says, "Yeah, I think I dropped my contact lens." And start looking, and after a while, student starts to give up. Professor says, you sure it was over here that you dropped it? No, it was about 50 yards that way, but the light's better over here. But Abelian groups have some things that make them easier to work with. any finitely generated abelian group is a direct sum of cyclic groups. And if it's not finitely generated, well, this isn't quite true anymore, but it's almost true. In particular, you can split off a torsion-free part. You can split off a part where everything has infinite order, and you can split off a torsion part. The group's going to be a direct sum of those. The torsion-free part is really impossible to understand. In fact, there's another really good talk I should give you sometime about the research, giving mathematical proofs that the torsion-free part is impossible to understand. But the torsion part is not so bad. There is a theorem from Ulm in the 1930s showing that as you go from finitely generated to countably generated, it doesn't get much worse than this. Yeah, you need a few transfinite ordinals, but what's that among friends? Abelian torsion groups, countable abelian torsion groups, are still relatively hard. We know a lot of stuff about them, and they're actually a very nice place to do computability theory. But they're still hard, and so usually when we know something non-trivial about abelian P groups, about abelian torsion groups, and there's another decomposition you can make to take even simpler blocks, most of the stuff we know about them, we got because we tried it out on equivalent structures first. And then it worked on equivalent structures. We said, can we actually do this with abelian groups? Yeah, sure enough, we can. So we look at structures that consist exactly of an equivalence relation. Even an equivalence relation on the natural numbers. Only restriction on the domain is that you shouldn't build any algorithmic complexity into that. You shouldn't cheat with what the elements of the structure are. So when we first started working on generically computable equivalence structures, initial results didn't look all that interesting. Now this result, and most of the results I say from here forward, are joint work that I've done with Doug Sinzer from University of Florida and Valentina Harazanov from George Washington University. And these are relatively recent things that I'm talking on today because I was proofreading the paper. So this says, if you have one of these structures that's generically computable, in the sense that you have a generically computable function to say whether two things are equivalent or not, then there has to be some infinite computable subset of the natural numbers on which E is computable. There has to be a big part that looks just like the classical world. Where you don't make any of these allowances for being wrong on small subsets. Okay. And if that was not depressing enough about prospects for this line of research, pick any equivalent structure you want. Okay, any countable equivalent structure, any equivalent structure on the natural numbers. There is an equivalent structure isomorphic to it that's generically computable. Now, drop generically here. It's no longer every structure. In fact, there's a really, really nice body of theory saying which ones do and which ones don't have computable copies. And here, yeah, everything works. The only non-computability you can get, at least the only isomorphism invariant non-computability you can get, is by contrived examples that you're never going to see practically. That was discouraging. But of course, one should not let discouragement get in the way of good mathematics. When we were proving this, the generically computable copies we were building were unsatisfying for a particular reason. If you take some equivalent structure, what it means for a subset of the domain to be faithful is that it respects the equivalence classes. And to make a generically computable copy, we were having to build things that seriously went against that. So the proof that all bad examples are contrived itself sometimes felt a little contrived. So we defined what felt wrong about it. And you can actually prove when you get an example that is nicer. Now, when you're looking at isomorphism of equivalent structures, a big part of it is about counting. This one has 12 classes of size 3, and that one only has 11 classes of size 3, so they can't be isomorphic. Now, the infinite equivalence classes are a different world. but the character of an equivalence structure, the character of an equivalence relation, tells you this form of information about how many classes of which sizes it has. And I'll give you the conditions. But here, here, if you start with an equivalence relation on the natural numbers, to get this theorem to be true, you have to pass to an equivalence structure whose domain is something properly contained in the natural numbers, and it may be a very awful subset that doesn't care about the equivalence relation at all. If you want to make that step in a way that cares about the equivalence relation, you have to meet some conditions. And here it starts to look like, okay, a very cleaned up version of the classical case, but it starts to look like the classical case. Either number one, okay, I will tell you what sigma 2 means in a minute. One way you can get that is if E has infinite equivalence classes. In computability, infinite stuff. Infinite equivalence classes, infinite order, whatever. Infinite stuff is very comfortable because if you're running some computation and you make a mistake, the infinite classes give you some place to hide your mistake. Oh, I meant to be building a class of size 3, and I found out that I shouldn't have been. I found out that there shouldn't have been another class of that size. Oh, no problem. I didn't promise you anything about its size. I'll just keep adding more elements, and I'll make it an infinite equivalence class. So having infinite classes means there's an easy way out. This one is a slightly less easy way out, but again, it's a condition on being able to take out the trash. So sigma 2 is a condition on being algorithmically not too difficult. Technically, what it means is that you can define that set of pairs. You can define it by using two quantifiers. The first one is a there exists, and the second one is a for all. And the more quantifiers you need to define something, the more complicated it is. You can see the truth of this if you think of whatever field of mathematics you've been thinking about most recently, and think of what concepts in that field you really need 12 alternations of quantifiers to define. Does anybody ever write anything that you really need? For all there exists, for all there exists, for all there exists. Do you really need 12 alternations of quantifiers for anything? 2 means you only get 2 quantifiers, so it has to be pretty simple. And this does look like a cleaned up version of when you have a computable equivalence structure. So things aren't quite as bleak as they looked here. Chapter 4. So if you have two equivalent structures that are isomorphic, isomorphic means that there is a function from the domain of one to the domain of the other that respects the equivalence relation and is one-to-one and is onto. An isomorphism is always a function, and so you can talk about how hard it is to compute that function. Famous example, if you take a field and then take its algebraic closure, the algebraic closure is unique, right? Take two algebraic closures of the same field, it's a standard theorem that there is an isomorphism from one to the other. But if you start with a computable field, you can build computable algebraic closures, two of them, such that there is no computable function witnessing that they're isomorphic. You really, really do need the axiom of choice for that, at least a little bit of it. So we say that a structure is computably categorical if any other computable copy, I guess I should say both of these are computable, there are things you can do if you drop that restriction, but they're not quite where I'm going. If you take any other computable copy of it, you should have a computable function witnessing that they're the same structure. A computable function witnessing the isomorphism. And that intensely does not always happen. On vector spaces over the rationals, for instance, the finite dimensional ones have this property. Infinite dimensional, no. In fact, infinite dimensional, at least in one dimension of failing to have this property, an infinite dimensional vector space over the rationals fails to have it as badly as you can fail. Now, back 2004, 5, 6, when Calvert and Shoup and all them were describing this generically computable stuff for the first time, where at that point were your heroes? Well, here's where we were. So one way it can be computably categorical is if it has only finitely many finite classes. Remember, infinite classes are practically free. You can dump any mistake you want to there. Alternatively, can have infinitely many finite classes, but only very, very carefully. You can have infinitely many of one size, but only one size, and you have to have a bound on all the finite sizes. So since we know how the computable ones work, it's reasonable at that point to say what happens when you replace computable with generically computable. Now, it is always permissible in a math talk to lie, just not to mislead. I'm lying to you slightly about what the definition of generically computably categorical is, but not in such a way as to mislead you. Now, need a definition first. So the generic character tells you the finite class sizes that matter, the ones that have positive density. And it tells you all of the ones that have positive density. So you can generically computably isomorphic is not a trivial concept, which is what you would naturally worry about having met that result, that everything has a generically computable copy. Not everything is generically computably categorical. Coarsely computable, that there are at least some natural examples that it seems like coarsely isomorphic is easier to come by than generically isomorphic. But those three question marks mark roughly the state of progress in the field, which seems like a good place to stop.
Any questions for the speaker? I have a few questions. From the last theorem, and then coarsely computable and generically computable, the one imply the other, or the other imply one?
Nope.
Or any intersection, some part intersection, or?
Yeah, those are the ones that, like I said, in the way of what examples you can make up, they have as little to do with one another as you could possibly want. There exist things that are both, there exist things that are neither, there exist things that are either one but not the other.
Okay. But anyhow, the bottom one is the computable function or computable set.
Computable is the weakest criterion, yeah.
Yes,
So,
and then
so if you're computable, then you're definitely generically computable and coarsely computable.
yeah, and then the two directions somehow.
Right.
Also, there is something which is neither some generically nor coarsely.
Yes.
Okay. I see.
I mean, either way, you have to count how many algorithms there are in the world. There are only countably many. And there are way more subsets of the naturals than that. So showing that there exists something which is not in whatever effectiveness notion you choose, showing that there's something that's complicated usually can be done with just a cardinality count. I don't know if you can quite get away with that here, but yeah, it's absolutely unsurprising that there are things that are neither coarsely computable nor generically computable.
Any other questions? All right, let's thank Wesley.